Okie dokie, chemists, let's get started. So we left off on chapter 12 on Tuesday. We may or may not finish this chapter today, but no problem. I don't want to rush us. I just want you to be aware that regardless of when we finish chapter 12, whether it be today or next week, the homework for this chapter 12 homework set is due on Thursday, December 7th. So yes, that means that this doesn't have the normal Monday due date, but Thursday, December 7th is actually the last day I will accept online homework at all. That includes any late problems. Do recall the late homework policy. Any unanswered questions can still be submitted for partial credit. Up until December 7th, all right? So do look through those previous homework sets. If there's one that you're missing, you can still get credit for that. You know, I get questions, emails all the time, you know, is there extra credit in this class? No, there is no extra credit, but any unanswered homework questions, those are automatic zeros. If you didn't answer or submit them yet, those are free points for you to earn that are still there for you to earn. So that's homework. Since we finished chapter 11 on Tuesday, that is due on Monday. SEIs are available. I'll announce that my final exam review session for the big one, the one that I do on Zoom, that one is on Thursday, December 7th at 1:30. So it's in this room and it's on Zoom. It's on your course calendar. This is reading day, if you didn't know. The last day of the semester is Wednesday, and then finals don't start until Friday. So you get a little bit of a breath of fresh air on Thursday, and that's when I put my review session, right? So you can come hang out with me on reading day. And then finally, do check those recitation grades and make sure you got 10s on the days that you attended, all right? So in order to get a 100% in the recitation grading category, you need to attend a minimum of 10 recitations, all right? So as long as you have 10 10s, then you have 100%. Right, so do check those because I want all grades to be finalized before our final exam. I'm hoping for December 7th, I want all those grades to be finalized. All right, so chapter 12, solids. So I mentioned before that our idea of intermolecular forces, covalent bonding, all coming together, us understanding it depends on the composition of the substance. The structure, so what kind of bonding is present, dictates a lot of the properties that we see. We are going to be studying crystalline solids because those are highly predictable. Amorphous solids are kind of more random in terms of their patterns, so they're harder to study. But the amorphous solids is a type of solid out there that you may interact with. But we're going to look at crystalline solids. We talked about the 4 different types of crystalline solids. We want to, in your back of your mind, you want to think about, okay, composition dictates structure and properties. So depending on the composition of the sample you're looking at, like if there's all metals present, then you're going to have a metallic solid because all metals are present. Metallic solids have metallic bonding because there are metals, and there's certain properties we'll look into what describes metallic bonding. Versus ionic solids. We identified ionic solids or ionic substances in chapter 2 when we named things, so don't forget those, all right? So, you know, bring those ideas back out of the crypt, but how we named ionic solids and how we identified them also helps us with this chapter as well. We recognized ionic substances contain a metal and a nonmetal that form cations and anions, and so those charges, the positive and negative charges, those attractions, we talk about that in terms of electrostatic attractions or lattice energy. So that's the type of bonding that's present there, lends itself to the properties that we see. And then the 2 weird ones are composed of all nonmetals, sometimes metalloids, where we have covalent network solids or molecular solids. We have really different properties present in these 2 types of solids because the bonding is different. In covalent network solids, all of the atoms are covalently bonded to one another. So when we compare the strength of a covalent bond, like a single bond, versus an intermolecular force, which one's stronger? A bond or an IMF? Which one's stronger? A bond, yeah, a bond is much, much stronger. They're harder to break. But IMFs are still kind of strong and they're important. They dictate a lot of properties, but that's what makes the difference between these 2 substances. Covalent network solids are composed of all covalent bonds, really strong bonds holding all of those atoms together, while molecular solids, the different molecules are only attracted to one another via IMFs, and that lends to the properties that we see. So IMFs are important in molecular solids, but the difference is, or kind of the confusing part here, is that both have all nonmetals present, so we need to be able to distinguish which one is which. So the properties that we see, it depends on the bonding that's present. Metallic bonds, there's this delocalization of electrons we'll talk about a little bit later, but these are the properties that you need to know and identify for metals. Ionic solids, because of the electrostatic, the lattice energy, we typically have very brittle, brittle solids because those ions can break from one another. But they're hard but brittle, and we typically have high melting and boiling points there because of those lattice energy attractions. When comparing covalent network and molecular solids, we have really big differences in properties here due to the nature of the bonding. Covalent network solids, because it's all covalent bonds holding it together, these are really hard materials, and they have really high melting and boiling points. Typically, these substances are not soluble in water because of those covalent bonds present. If you dissolve it in water, water cannot break those covalent bonds. So maybe I should write that here. Covalent network solids, typically non-soluble. On the other hand, molecular solids, these substances, usually they can be soluble. They're more likely to be soluble, I guess. More likely to be soluble. So for example, like table sugar. Table sugar has a chemical formula. You can pick up one sugar molecule, but when you have a sugar sample, there's billions and trillions of sugar molecules all attracted to one another via IMFs. Does our intuition tell us does sugar dissolve in water? Yeah, sugar does dissolve in water because when you put sugar in water, all you're doing is breaking those intermolecular forces, versus covalent network solids do not do the same. So what we typically see with molecular solids, these are soft due to the nature of the weak intermolecular forces. If they do dissolve, sometimes there's poor or no conductivity unless you dissolve like an acid or a base. Those substances can conduct electricity when it's dissolved in water, and typically these molecular solids have low melting and boiling points, again, because only IMFs are holding this substance together in the solid phase. All right. So those are all the properties. So let's put them all together and determine, based upon these descriptions, and these are more like exam-like questions, okay? I give you descriptions. Tell me what kind of solid this is based upon the description. Okay, so the first one, we have a solid that is soft at room temperature. It's very soluble in water and whose aqueous solution does not conduct electricity is most likely to be a what? So it's soft, so let's think about that. Soft. Soluble in water. So what do we think? Just go back to the previous slide. What do we think? What do we think? Which one is soft? Molecular solid, yes, molecular solid. Very soluble in water, whose aqueous solution does not conduct electricity. So this could be something like sugar, like glucose or something. Table sugar is actually sucrose, but whatever. C6H12O6, solid. Right, so like regular table sugar or whatever, like this is a molecule. It's composed of all nonmetals, but all the nonmetals are just bonded to one another. Once we put a lot of sugar molecules together, those different particles are only attracted via IMFs. So that's why the solid is soft. That's why we can typically dissolve this in water, because those IMFs can be broken. And so if this was chapter 4 and I said, oh, you have an aqueous glucose solution, and I asked you what kind of conductivity would you observe here, what would you say? And how did you determine that? If to look at conductivity of this substance. This is review of chapter 4, which, remember, our exam is cumulative. So aqueous glucose, does that conduct electricity or not? No. And so how did you know? All nonmetals, yeah, so remember that idea is coming back. All nonmetals, this does not produce any ions when you put it into solution when it dissolves. And so that is consistent with all of those factors we just looked at here. Okay, next one. The solid is shiny, malleable, completely insoluble in water, but whose solid conducts electricity is most likely to be what? Metallic, yes, that is our metallic solid, so it's a metal. We know metals, pure metals like copper, iron, those pure metals do conduct electricity due to delocalization of electrons, which we'll talk about a little bit later. Okay, and the last one, it's worded a little bit differently. At room temperature, sodium bromide is expected to be a what? So this one's a little bit backwards. This time I give you a substance. From the formula, you should be able to tell me what kind of solid this is, which one of the four this is. You can also ask yourself, how did I name that? Sodium bromide, like what kind of naming scheme did I use? That's ionic. So this sodium bromide is ionic because I named it sodium bromide. It's made of a metal and a nonmetal, just like how I named it. So we want to pick which of these properties best fits ionic substances. Are ionic substances typically gases at room temperature? No. What about liquids? Nope. Does sodium bromide solid conduct electricity? No, the solid does not, but sodium bromide what does conduct electricity? Aqueous. Once it's in water, now the ions are free, it can conduct. All right, and so which one's the right one? D, yes, it is a brittle solid. Soft solids would be molecular solids, like glucose or whatever. Okay, so that is, taking those previous two slides, connecting, the composition of the substance. Can you determine just from the formula whether we're working with metallic solids, ionic, covalent, covalent network, or molecular solids? And then relating that to the properties that we observe. Okay, so those are the properties of the types of solids. Now let's look at the crystalline nature of solids. We discussed gases in terms of, kinetic molecular theory, observing them and their properties via Pivnert. Liquids, we looked at their boiling points. So solids, on the other hand, because of their crystalline nature, there's a lot of properties that we can predict and study within solids. Mainly what we call unit cells and the patterns in which solids adopt. So these these solids, when they're highly ordered, we can kind of categorize how the atoms actually put themselves into three-dimensional space. There's lots of different ways you can pack a solid into 3 dimensions. So we use what's called unit cells to describe these crystalline solids. So what a unit cell is when you have a crystalline solid and the extended network of atoms repeat itself, what we want to do is look for the smallest repeating unit. It's kind of like a wallpaper. You ever wallpaper isn't really in anymore, but if you look at a wallpaper, sometimes you can find what is the smallest repeating unit inside that wallpaper that you could repeat a million times, an infinite number of times to get that pattern that you want. And that's essentially what a solid does. You look at the solid as a whole, how all of the atoms are arranged, but you want to find what is the smallest repeating unit that you could repeat to get that same structure. That's what a unit cell is. So solids are composed of an infinite array of these unit cells. And so there's a couple of, here's a couple of examples of unit cells. It's not a learning objective for you to memorize these. I just want you to be aware that these exist, all right? So how we look at these unit cells is that the atoms are the black dots that you see, and the black outline is the repeating unit that we can put in this arrangement, in this array, to get this certain arrangement of atoms. So we see, okay, if the atoms are all arranged this way, the unit cell would be a perfect square. So we call this a square lattice unit cell. Versus if the atoms are kind of more diagonal in nature, then we have this oblique lattice where now the repeating unit isn't a square, it's actually a, what kind of shape is that? A parallelogram. Is that what that's called? Okay, yes, a parallelogram. Or we could have a rectangle, depending on the spacing of the atoms themselves. Of course, this is all specific to the actual solid sample that we're looking at. And some other weird ones here is this hexagonal lattice. This one's kind of harder to see, but we do see that the repeating unit is a hexagon. Right? And so, identifying what is the simplest repeating unit, that is our unit cell. Because technically, couldn't we, if we looked at the square lattice or something, you might think, oh, this is your repeating unit. Because if I repeat that, the 4 arrangements of atoms, won't I get that shape? If I repeat it like 1, 2, 3, 4, I should get that same shape. But is that the simplest shape? No, it's not. So we can even simplify it even more. So those are 4 of the 2-dimensional lattices that we can have. All right? But here's the thing. Are solids 2-dimensional? No, it's not. So if you're in engineering, you will see 3-dimensional unit cells and space groups one day. Okay, solids, they do not exist in 2 dimensions. They actually exist in 3 dimensions. So we don't just have 2-dimensional unit cells. There's actually 3-dimensional unit cells because we actually want to repeat these solid shapes in 3 dimensions. It's not just a flat wallpaper. So here's some other examples of we can take those 2-dimensional unit cells and extend them into 3 dimensions. But the same concept is still there, that the black dots in the single unit cell, that is an atom. And again, we're trying to find the simplest unit that we can repeat to give this extended 3-dimensional network. So what's kind of interesting is I've been having trouble sleeping because I was thinking about space groups and unit cells in preparation for this exam. And I mean, you might think, oh, I'll never see this ever in life, but you might here soon. So like when it snows, it's very pretty to see snowflakes, And I was just thinking about this. Have you ever made a paper snowflake? When was the last time you made a paper snowflake? Right? Just think of maybe yesterday, I don't know. Just think about how you do that, right? I wish I had a piece of paper. You take a piece of paper, right, and you fold it in half to make a paper snowflake. You fold it in half, so there's 2-fold symmetry. And then you fold it in half again, so then there's 4-fold symmetry. And then you fold it in half again, right? So then there's 8-fold symmetry, and then you cut out the things and you unfurl it. Right? So when we make paper snowflakes, there's actually 8-fold symmetry in it. But the problem is that water is actually, ice is a molecular solid. It has a crystalline structure that we see in snowflakes. Snowflakes have 6-fold symmetry. They are in a hexagonal unit cell. So whenever you go home and make Christmas or holiday decorations and make snowflakes, and you're folding your piece of paper, to make 8 folds, know that that's actually incorrect, and you should be making 6 folds because snowflakes have 6-fold symmetry. They're in the hexagonal space group that you see here, all right, in 3 dimensions. And so water, when it freezes, it becomes a molecular solid. Snowflakes only really form when the crystals can form very slowly. Because if the crystals form very slowly, it gives those water molecules enough time to orient themselves to make these really nice, intricate snowflakes. But if it gets cold too fast and we just see a flurry, then the crystals just kind of become all gloopy, and you don't actually see distinct snowflakes. Crystallization is this huge field of chemistry. You always want to make really nice crystals. You gotta cool it or make the crystals very, very slowly. And actually another analogy, you ever make what's that called? Rock candy? You ever make rock candy? Yeah. You take sugar, you dissolve it, and you put a little piece of string in, right? And the whole idea is you want the crystals to form really slowly, because if you do, then you get those really nice crystalline rocky formations. But if you form it too quickly, then you just kind of get this gloopy mess. All right, so those are some ideas of crystallizations. What you're seeing are forming of crystalline solids there. Okay, so yeah, don't need to memorize these, just know that they show up in solids. Okay, so how else can we pack atoms in a space? There's actually a lot of ways. You might not have thought of this, how to pack atoms in 3 dimensions. So atoms, they can in fact pack differently in 3 dimensions. So we're looking at three different types of unit cells, and they have different names. So the first one you see here is called a primitive unit cell, where how we pack atoms in a space is kind of on top of one another. So like here are 4 atoms on the bottom, and you see it in the picture, and then you put the same 4 atoms directly on top. So packing spheres, if we assume atoms are spheres, it's actually not super efficient to pack atoms in this way, because you're putting like the, how do I want to say it, like the peak of one sphere on top of another peak of another sphere. So primitive unit cells actually is not super efficient in terms of packing. Here's the same cubic unit cell blown up. We have an atom in every single corner of this cube. Or you can think, okay, 4 atoms here, 4 atoms on top, directly on top. Right? So that's our primitive unit cell. Another type of unit cell we can have is called body-centered cubic. I have these in the wrong way, wrong order. Okay, my boxes. Okay, body-centered cubic, where we take a primitive unit cell. Okay, so you see that we have the 8 atoms on every single corner, but then we add an extra atom in the space between all 8. So body-centered just means, oh, you have an extra atom inside the unit cell sitting in the body. So you can see it's right there in the body, or sitting there inside that box. Yes. Yes, it's not floating. There's like a piece of glass in there that's keeping it, elevated. So that's body-centered cubic. So what we see going from our primitive unit cell to our body-centered cubic unit cell is that we're increasing the packing efficiency. Soon here we'll count how many atoms are actually inside this box, inside this unit cell. We can count how many atoms are inside this unit cell, and what we're doing is increasing the efficiency of packing. And then our last one here is called face-centered cubic, where it's the same idea. We start with the primitive, but now face-centered just means that we have an atom on every face of our cube, our unit cell. So how many faces are on on a cube, on a dice? 6. So we're adding an additional 6 atoms across this unit cell where it's sitting on the face of each of those. And so this also increases our packing efficiency. It looks like this. We always start with atoms on every single corner, and then for face-centered cubic, we add an additional 6 atoms on those faces. So those are different ways we can pack our atoms in 3 dimensions. All right, and so what we see here, primitive has the least efficient packing, body-centered more, and face-centered cubic even more efficient packing. Okay, all right, another way we can think about packing atoms in a space is thinking about like layering atoms in a box or something. So if you think of atoms like a sphere, let's pretend we wanted to pack atoms inside of a box. So we would lay a bunch of spheres on the bottom of our box in this nice, uniform layer. So that's what this first step is, layer 1. Let's fill our box with these gray atoms where they're all packed as efficiently together in one layer. Now let's say we want to add more atoms, add a second layer of atoms to this box. So what's kind of interesting here is once we have the first layer, we actually have 2 choices of where we can put our B atoms. So in this example, there's different sites on top of our A layer atoms. So when you have like 3 atoms next to one another and they're all spheres, there's a divot right here. And so it would be perfect for that second layer is to put another atom right here in this divot. So if I put 1 atom right here in this divot, my next atom, it can't go into this divot. It actually has to go into that divot. So if we add our second layer of atoms, if I start on what is this red site, all of the rest of that layer will go on the red sites there, all right? And so that's what this second picture is trying to say. Okay, here's your first layer, here's your second layer of atoms. And what kind of gets interesting here is now once we get to our third layer of atoms, we have 2 different choices of where to put that third layer of atoms. So there's 2 different patterns, an A-B type of patterning, where the third layer actually is directly on top of that original first layer. Or we can have an ABC type patterning where the third layer is actually in a new unique spot, a new unique layer above that first and second layer. Here's the side view that might make it look better. Here's the first layer, second layer, and the third layer. So the first layer is here. You see the second layer is offset, but the third layer is directly on top or equivalent to what that first layer was. So that's why this is called ABAB type packing, where the first and the third layer match exactly. They're right on top of one another. But where things get different here is the ABC type patterning, where here's your first layer, here's your second layer, but your third layer is actually in a spot that is unique to that first layer. So this, oh my gosh, is my pen dead? I'm gonna be really mad if it's dead. That C layer is in a different position that is not equivalent to that first A layer. Am I dead? Yes, I am dead. Yes, so that's where we get this ABC type layering. So that third layer is in this new unique spot. All right, so this different patterning, ABAB, we call this hexagonal close packing, and then the ABC type layering of packing of spheres, we call this cubic close packing. And so these two packing structures have the same packing efficiency, and what we see here is that if we looked at the unit cell of a cubic close pack, it's actually the exact same as a face-centered cubic unit cell, right? So those are the ways we can pack atoms into a space. Okay, so let's now talk about, so we talked about unit cells, how we can pack atoms. So now let's go into the different types of solids that we talked about earlier: metallic, ionic, molecular, and molecular, and then covalent network. So first we'll talk about metallic solids, where the properties come from, and the different types of metallic solids. So the first type of metallic solid we can have are just the pure elements. All right, so if we're talking about pure elements, then all we're doing is packing copper atoms. All we're doing is packing gold atoms in a space, right? And it's all the same exact, like every single one of these spheres is the exact same atom. Simple, all right? And they can have different unit cells, different packing efficiencies there. So if you look at like a copper sample versus a gold sample, they may have different unit cells. They may have different ABC, AB type patterning, all right? That's something you would look up. You don't have to like know the difference or memorize the difference between gold and copper. So those are elemental metals, the one element, pure elements, same atom repeated in our unit cells. But more commonly, I guess, in our world, we actually don't really interact with pure metals very often. We actually interact with alloys that usually contain more than one element. Alloys are a mixture because their composition is usually given as a percentage. And so there's two types of alloys that we can have. And the two types are substitutional alloys and interstitial alloys. So I'll describe the difference here. So an alloy, you need at least two elements present. They're mixed together, but there's actually different ways we can mix them. The first one, substitutional, is exactly how it sounds. Substitutional alloys, like an example would be bronze or brass, is we take the unit cell of like copper, all right? Let's say like this is copper, all right? And we wanted to make bronze, so we add some tin atoms, but there's actually different ways we can add the tin atoms. If I just replace some of the copper atoms with tin, that is a substitutional alloy. You're substituting one element in the unit cell for another element. And that's what you see in this picture right here. This is for 14 karat gold. The unit cell is mostly gold, but you see, oh, some of those gold atoms are just replaced with silver atoms. We don't see a big disruption in the ordering, the lattice of this solid. So some examples of substitutional alloys: bronze and brass. Both of them start with copper unit cells. We just substitute other elements there, inside there, to either change its properties, typically strength, or what have you. All right, the other type of alloy is called an interstitial alloy, where, here's an example. So steel, stainless steel is an example of an interstitial alloy, where we start with an iron unit cell. And so what makes stainless steel, steel different from iron is that we add copper, or it's not copper, sorry, carbon to the substance. So we have a mixture of iron and carbon, but the difference here is carbon doesn't replace the iron atoms. What can we tell from this picture? The carbons are just in between the voids, in between the spaces of the iron atoms themselves. And so that what makes the difference between substitutional and interstitial alloys. We have two elements present, but how they replace one another inside the unit cell, it differs. Substitutional do replace one another, while interstitial, the added element lives inside the voids of that unit cell instead. All right, so there is steel. You just have carbon atoms spread throughout the voids of the unit cell of iron. And we can do this because iron is a fairly big atom, but carbon's really small. You can look, they're in different rows, right? So if carbon's really small, it would make sense that carbon would go into the voids of iron because the irons are so big. Substitutional alloys, you'll see more typical when the atoms are more similar in size. Yeah, because they can replace one another, but not in steel. Okay, so that's alloys. Composition is usually given as a percent. These are mixtures. A different type of metal is called an intermetallic compound. So these compounds are typically given as a formula. So for example, here this is like aluminum 1, 2, 3, 4. I think this is like Al2 nickel 1 or something like that. So we could try to communicate the composition of this substance using a chemical formula, where the ratio is more set in stone. That in this example, there are 8 aluminums for every, oh no, it's written right there. I'm so dumb. Yeah, sorry, it's 3. I was trying to count it in my head, but I couldn't do it very well. Nickel. Oh yeah, it's right there. So here they're trying to say, oh, there's 3 nickels for every 1 aluminum. Here we have a compound where the ratio is set. So that's why we call this an intermetallic compound. That formula is given as a compound. So the lattice of atoms in the unit cell is more defined than the randomness that we see in substitutional or interstitial alloys. So for example, in this picture of an alloy, see how the other element is kind of like randomly put in there? You would talk about the composition here as like a percentage because it's not super uniform. Versus in an intermetallic compound, we see that the ratio of blue and red atoms is set in stone. So this has more compound properties. And so that's the difference between intermetallic compounds and alloys. The substitutional alloy is more random in terms of the substitution, but in a intermetallic compound, that unit cell is more set in stone in terms of the atom ratio. Okay, so those are our metal solids. Okay, so let's talk about metallic bonding. So earlier in the slides, we looked at some of the properties of metals, including metals like, copper, iron, whatever, conducts electricity. Typically, metals have variable melting points, but some of their interesting properties includes you can, work with metals, right? You can bend them. They're ductile. They're malleable. All right, and this has to actually do with some of the properties we talked about earlier. Metals, right? Metals on our periodic table, they typically form what kind of ion? Metals form what? Positive, which we call cations. Metals form cations. The reason metals form cations is because they typically have low ionization energies. The reason, if we go like left to right across the periodic table, if we go from like potassium to bromine, potassium forms a cation. Bromine forms anions. If we move left to right across the periodic tables, how does size of those atoms change? Potassium is what, big or small? Big, while bromine is smaller. Yeah, so if we think about ionization energy, is it easy to take an electron off of potassium? Yeah, because it's big. And so that's why metals, because they're all on this, the left side of the periodic table, they're bigger, they have low ionization energies, it's easy to take off electrons. That's why they form cations. This idea also lends itself to why metals conduct electricity. This is called the sea of electrons theory, that, you know, if we have a sample of metal, all of those metal atoms, they all have low ionization energies. All of them have valence electrons that are easily lost. So all of them basically give up their electrons, and they're shared amongst everyone. So here's an example. This is silver, all right? Silver has one valence electron based upon its electron configuration. So when we put a bunch of silver atoms together, all of them give up that one valence electron, and they share them amongst all of the silver atoms, because that one valence electron is easily lost. Typically, when we talk about valence electrons, we think they're easily lost. And so that's why metals conduct electricity, because they have these low ionization energies. Once you put a bunch of those atoms together, they all kind of have weakly attracted electrons that can easily conduct electricity when you put a load against it. All right, so yeah, you can think of the blue electrons you see here, those are those mobile valence electrons that are easily lost, while the pluses, those are your actual silver atoms. All right, so the sea of electrons theory explains some things. It explains why metals conduct electricity, because those electrons, the sea of electrons, they're delocalized across those atoms because of the easily lost valence electrons. It also explains why metals tend to be malleable, because if you take this picture and you move the, you know, the atoms away from one another, if you try to like bend this picture, all right, and you bend where the atoms are, you're not breaking individual bonds. You're just kind of like moving the electrons around. Since you're not breaking individual bonds, we typically see that metals can be easily bent without like disrupting or completely breaking the material, because these positive nuclei just kind of move past one another, but it's still in this sea of electrons. All right, so the sea of electrons is kind of like a simple theory we can use to describe some of the properties, but it's not the true theory to explain all the properties that we see. So what we actually want to use to describe some of the other properties that we see in metals includes what's called band theory. So band theory is just a very sophisticated molecular orbital theory. All right, but it's specific to atoms, all right? So here's the trend. This is how we can, if we just memorize what the melting and boiling points and stuff are for metals, the trend is for melting points of metals is melting point decreases as we go down a group. So when we go from sodium to potassium to rubidium, all right, atoms get bigger, melting point goes down. Right? So the idea here is smaller the atom, smaller the metal, the harder it is to melt. That's the trend here, all right? Small metal atoms form strong metallic bonds, therefore have the highest melting point, all right? So it's easy enough to predict melting points going down a group, because as we go down a group, N just increases, that's it. But what's different is, okay, how can we predict melting points going across a group, or across a period? That's harder. All right, so the trend is, especially with transition metals, what we actually see when we move across a period, such as the transition metals, is that as we go across like the 3D block, we see that as we go from titanium to chromium to manganese, boiling point or melting point temperature goes up, but then once we get to like cobalt, nickel, copper, melting point goes back down. Right, so that's kind of weird. So across the D block, we see melting point go up and then melting point go back down. This can actually be described by band theory or MO theory. So the sea of electrons model cannot predict this. So this is what's happening, all right? This is what's causing this increase in melting point and then decrease at the end, all right? Okay, so this is a little bit of review. If I combine two atomic orbitals, how many molecular orbitals do I get out if I combine two of them? 2, yes. If I combine 6, so 3 and 3, 6 atomic orbitals, how many molecular orbitals do I get out? 6, yeah. If I combine a total of 100 atomic orbitals, how many molecular orbitals do I get out? 100, yes. Okay, but in a solid, how many atoms are in a solid? A billion. Billions. So if I combine a billion atomic orbitals, how many molecular orbitals do I get out? A billion, yes. And so this is the big idea, that as we increase the number of atoms that we're combining their atomic orbitals, right? So here's an example. Number of atomic orbitals. Here's just the 2 MOs that we get. 3 atomic orbitals, there's 3. See how they're actual discrete levels? But as we increase to an infinite number of atoms, we have an infinite number of these energy levels that we could put in electrons. And so we call this band theory, because the energy levels, they're so close together that it's not just like, you know, when we talked about like sigma and sigma star and stuff like that. All right, these were discrete energy levels that we could put 2 electrons in each of them, like 2 there, 1 in there, whatever, right? But once we have a billion molecular orbitals, they all kind of smush together and form what we call bands, where the bottom of the band, when we talk about molecular orbitals, the lower molecular orbital, we call that a bonding orbital. But then what do we call the upper orbitals? Antibonding, yes, all right? So the same ideas here for metals and band theory. The bottom band is a bonding, band within a metal, and then the top one is antibonding. And the same rules apply. Add electrons to bonding orbitals, you strengthen the bond. But if you add electrons to an antibond, what do you do to the bond? You weaken it. And so that's actually what happens here, all right? So when we think about metals, all right, when we compare like titanium, vanadium, chromium, all right, as we go across the period in our transition metals, what we're actually doing is adding more electrons to our MO diagram. So here, this is an example. I put the electrons in for titanium. I put them in a bonding orbital, so that strengthens the bond. But if we look from titanium to vanadium, vanadium has more electrons, so don't I have to put more electrons into this MO diagram or this band theory diagram? So if I put more electrons into a bonding orbital, what do I do to the bonds? Strengthen it. So if I add more electrons to the bond, strengthen the bond, how do you think melting point changes? Do you think it gets easier or harder to melt something when the bonds are stronger? Harder. So that's why as we go from titanium to scandium to chromium, we see melting point increase because we're adding electrons to a bonding band, all right? Then we move from, you know, vanadium, chromium, okay, chromium, even higher melting point temperature because we're strengthening the bond, but something interesting happens when we get to the middle of the periodic table. All right, so once we get to the middle of the periodic table, all right, so let's say for cobalt, all right? Cobalt, I add 2 more electrons when I move to cobalt, but this time instead of adding those electrons to a bonding band, I'm adding to them to the anti-bonding band. All right, so for cobalt, when I added those 2 electrons, how did the bond strength change? It decreased, so how does that change the melting point? It decreases, yes. So that's the whole idea. Once we get to the second half of our D block, now we start putting electrons in an anti-bonding character band. We weaken metallic bonds, we lower the boiling point temperature, or melting point temperature, sorry. All right, this looks similar to something you've already seen, all right? This isn't totally new news to you, where, okay, we add electrons, we strengthen the bond, we get too far, and we start to weaken the bond because we add electrons to anti-bonding orbitals. It actually, this picture said the same thing. You remember how to calculate bond order for MO diagrams? So it's a little bit of a review, all right? How do we calculate bond order using MO diagrams? Bonding electrons, minus anti over 2. So let's look at the P block trend going from boron to fluorine or diatomic neon. So here we see boron, diatomic boron has 2 bonding electrons. All right, I'm just going to ignore these bonding and anti-bonding pi or sigma and sigma star, because these two will always cancel each other out in all of these pictures, like the 2 bonding, 2 anti-bonding. So here in diatomic boron, the bond order is 1 because it's 2 over 2 equals 1. But when we move over to diatomic carbon, we're just adding 2 more electrons to the MO diagram because we moved 1 atom over. So we see, oh, now we have 4 electrons divided by 2. Bond order is 2. Bond order in diatomic nitrogen is what? 3. So we see as we are going across the periodic table, bond order, bond strength is going up. But then what happens once we get a little past halfway? Oxygen, we add 2 more electrons, but now those electrons go into an anti-bonding orbital. So we see now we have 6 bonding electrons minus 2 anti-bonding electrons over 2. Bond order of oxygen is 2. So now bond order is going back down. For fluorine, it's 1. And diatomic neon, which doesn't exist, is 0. So we see the same thing. Oh, bonds increase, bond order increases, bond order decreases. And we see the same thing also in transition metals, but the only difference is here we can take it further, relate the strength of metallic bonds to its melting point instead. All right, so you have seen this before, I promise. So the difference in band theory is we just have an infinite number of these orbitals, that the bottom half of the orbitals that they can occupy are called bonding, these bonding orbitals, and the top are anti. But it's the same idea. Okay. All right, so those are our metals. Okay, metals. So now let's work our way over the periodic table and understand that depending on the composition of your solid dictates what kind of bonding you're going to see. So in metals, we actually see like aluminum, a sample of aluminum has a lot of different, makes a lot of different metallic bonds with other aluminum atoms. But as we move towards the right side of the periodic table, we actually see less bonds are required to fulfill atoms' octets. So when we go from group 4, 5, 6 to 7, we see that we start to form covalent network solids when we have some of the lower valence electron count nonmetals, but once we get to groups 5, 6, and 7, we actually form molecular compounds because there's less bonds that are needed to fulfill octets. Right? So this is the whole idea of, molecular and covalent network solids are both made up of nonmetals, but depending on how many valence electrons are present, do we make a extended network of covalent bonds, or do the atoms actually just bond to one another and form a solid via intermolecular forces? So if you think about the periodic table, where your elements lie, you can predict what kind of solid is made. All right. So we talked about metals, so let's go on the other end of the spectrum here and look at molecular solids. All right, molecular solids. We have discrete molecules that are formed from covalent bonds, so that's like Lewis structures, Vesper theory, whatever. But they're a solid because the intermolecular forces have taken over and all those particles are attracted to one another in the solid phase. So when we look at properties, we're just looking at intermolecular forces. All right, so in the solid phase, these intermolecular forces, we can also consider them, call them van der Waals forces. This is what prevents the particles from moving past one another, like in the liquid phase, right? And so remember, these intermolecular forces are really, really weak. So that's why we have soft materials. That's why we have low melting point materials. If we look at this picture of solid H2O or ice, these bonds between the oxygens and the hydrogens, those are strong. Those are covalent bonds. But when we take a solid and we melt it, what we're actually breaking are these weak dotted lines, the intermolecular forces between the actual molecules themselves. All right? So that's the difference of when we melt something in a molecular solid. Molecular solids, we're just breaking intermolecular forces. When we melt metals, we break metallic bonds. Those are stronger, so that's why we see higher melting points. So here's an example. I just want to showcase, like, This is an example, this could be an example of like a metal or an ionic salt, where we have this extended lattice of atoms. But in a molecular solid, this is kind of harder to see. This is solid CO2. Because if you look closely at the structure, you can see a discrete CO2 molecule in there. This is CO2. So there's just a bunch of these in this structure, all kind of crammed together. Each of these particles are crammed together. They're held together via intermolecular forces. Versus in these structures where we have, these could be metal atoms or something. These could be metallic bonds, or these could be ionic bonds. Those are much stronger, right? Those types of bondings are much stronger than the bonding that's holding these CO2 molecules together in the solid phase. All right, so that's why molecular solids have lower melting points, and somewhat soft, because IMFs are what's keeping them in the solid phase. When we melt stuff, when we melt molecular solids, we're not breaking the covalent bonds, we're only breaking those IMFs. Okay, so let's circle which interaction is broken when we melt ice. It's these pink little squiggles. We're just breaking those dotted lines, right? We're not breaking covalent bonds. Okay. All right, graphite, molecular solids, we typically look for all nonmetals. Graphite, which is just carbon, is another example of a somewhat molecular solid. It kind of is both. Graphite is an example of a molecular solid where the atoms are held together by some intermolecular forces. So graphite, pencil lead. We use graphite as pencil lead because it forms thin black sheets when we write across it. I haven't used a pencil in a long time. Across a sheet of paper. And so the reason we use graphite is because of its structure. So graphite has these sheets of carbon atoms in a trigonal planar arrangement. So each of these carbons are sp3 hybridized, where all of these carbons, those are our covalent bonds. All right, all the bonds between these black atoms, those are covalent bonds. So when we draw, when we use a pencil across a piece of paper, do you think we break those covalent bonds? When we draw across? Nope, we don't. We probably break the weaker intermolecular forces. So in graphite, graphite is composed of a bunch of these sheets. The carbon atoms that form these sheets, those are strongly held together. But between these sheets, let's pick a different color. These red lines, these are weak intermolecular forces that can be broken easily. So these are the interactions, the green ones are the ones that's weak. So when we can just, use physical, mechanical friction to separate the layers of graphite because the intermolecular forces are very, very weak. Versus the carbons that make up the layer, those covalent bonds are very strong. So this graphite is an example of a compound that's kind of both molecular and covalent network, where you have a network of carbon atoms in each layer, each sheet, but between the sheets you have weak intermolecular forces that are more molecular in properties. All right. Okay, so that's graphite. All right, so let's talk about other non-metal compounds, but this time they don't have intermolecular forces. So if there's no intermolecular forces present in a compound, all you have are very, very strong bonds, like covalent bonds, then you're going to see higher melting points, you're going to see higher boiling points, you're going to see really tough, rugged materials in general. So covalent network solids, again, composed of all nonmetals, but the bonding is different. It's all covalent bonds. So there's no intermolecular forces, so you do see elevated boiling points and so forth. All right, so no IMFs here. So here's an example. I think this is diamond. So here, in this picture of diamond, each carbon atom is attached to 4 other carbon atoms. Everything is connected by a very, very strong covalent bond. There are no intermolecular forces present in this diamond picture. Versus if we look at graphite, you tell me, is graphite different than diamond in terms of its properties? Yes, it is. And the reason is because its structure is different. In graphite, we have those weak layers of intermolecular forces between those layers. So we have different properties. But diamond, on the other hand, very, very high melting point, because in order to melt diamond, you would have to break all of those covalent bonds. Each carbon is attached to 4 other carbons. So you have to break a bunch of covalent bonds to melt diamond in this case. So diamond, which is carbon, has a very, very high melting point. The structure, again, all covalent bonds are there, lends itself to its high melting point. Silicon dioxide is another example of a covalent network solid, or this is like glass or quartz. You know, oftentimes, I guess, like, you know, diamond and quartz, they can be mistaken, or not mistaken, but like both thought as cool gemstones to look at, cool, shiny gemstones. Silicon dioxide, silicon is a semi-metal or a metalloid, but oxygen is a non-metal. So silicon dioxide can also form covalent networks because silicon is a non-metal, a semi-metal, and still falls under that covalent network solid idea. So glass or quartz also has a very, very high melting point. Okay, very, very high. Something about covalent network solids, I mentioned this before, they're insoluble in water or all solvents, again, because of those strong covalent bonds that are there. Okay. Those are covalent network solids. So what's next? Okay. Ionic solids. Ionic solids, they are made up of cations and anions. All right? So typically what you're looking for is a metal and a nonmetal. So these ionic solids, we have to think about the electrostatic attractions between the cation and anion together, the lattice energy holding them apart. Their melting points are also usually pretty high, like above 500, but usually not as high as covalent network solids. Ionic solids have very high melting points, but not as high as just all covalent bonds. All right? So ionic solids, we know if they're in the solid phase, those ions are not mobile. So like this is an example, this is salt, this is NaCl, where half of the atoms are sodium, half of them are chlorine. If this is salt in the solid phase, these ions can't actually move. So if I put an electrical bias here, these ions can't move. So this is actually an insulator. It doesn't conduct electricity. But as soon as I put this into water, we know that NaCl is a strong electrolyte. Those Na plus and Cl minuses, they're free to move around. Now NaCl aqueous does conduct electricity. And so all salts are like that as well. As long as a salt is even a tiny bit soluble in water, it will conduct electricity. But any salts in their pure form, solid phase, will not conduct electricity, right? Unless I take this salt and I melt it. If I melt it and make it molten, which isn't super common, like I don't just go home and do that, then it will conduct electricity, because once it's a liquid, then those ions can move past one another, and it does conduct electricity. Okay, all right, so so let's review. Let's compare the conductivity of these things. NaCl solid. Is it conductive? No, why? Because it's a solid. Ah, oh, stupid pen. All right, solid. It does not conduct. What about the liquid form? Does it conduct? Yes, it does, because at that point you do have free ions. What about the aqueous form? Yes, yes. Yeah, so it doesn't mean all NaCl conducts, only when you have free ions present, all right, or movable ions. All right, other examples of ionic materials. Gemstones. This is my favorite part of 1210 in this chapter. Now we just talk about pretty things, gemstones, okay? Ruby and blue sapphire, they're both ionic solids. They're made of mostly corundum, which is aluminum oxide, right? But the difference between ruby and sapphire is that there's a little bit of an impurity in the structure of the aluminum oxide. You can think of it like an interstitial alloy. There's like a little bit of a substitution of some of the atoms in there that make these beautiful colors. All right, so really ruby is red and sapphire is blue because of the impurities in aluminum oxide, which makes it valuable, because you're looking for very certain types of impurities to get these specific colors. So ruby contaminated with a little bit of chromium, and blue sapphire is a little bit of iron and titanium. So it's like the earth had to, just so happen have those impurities around when forming them in the earth. So let's compare some diamond alternatives, all right? Or let's compare, shiny gemstones. So let's compare some covalent network solids and ionic solids in gemstones, all right? And I'll explain to you why I don't buy diamonds, for ethical reasons and for chemical reasons that we'll learn about right now. Okay, so diamond, that's like the gold standard. Every girl wants a diamond, I guess. But some of the other alternatives out there include moissanite and maybe even cubic zirconia. So let's look at those. And structurally, let's think about this as chemists and think about the differences here. So diamond is composed of pure carbon atoms, all right? So we classify this as a covalent network solid. All right, I personally purchase moissanite. It looks just like diamond. And all I do is take half of the carbon atoms in the structure and replace them with silicon atoms. That's it. So you look at where silicon is on the periodic table. It's just the big brother of carbon. So I'm just replacing half of the atoms, carbon atoms, with silicon to make moissanite, all right? And then finally, cubic zirconia is zirconium and 2 oxygens. I would classify this as an ionic compound because zirconium's a metal, oxygen's a nonmetal. But moissanite, on the other hand, silicon and carbon, we have a metalloid and a nonmetal. So I think that would fall under covalent network too. So here are 3 pictures of diamond, moissanite, and cubic zirconia. Can you tell them apart? Can you tell them apart? No. See, my simple monkey brain, I just like shiny things. And so I need to remember, I think this is in alphabetical order. So this is cubic zirconia, diamond, moissanite. That's the order, right? Yeah, did you think that? Now let me give you the prices. All right, you want to know the prices? Yes, okay, so for a 2 carat of all of these, I didn't write this down, I have to memorize it. 2 carat, which is about I think 8 millimeters across, all right, gemstone. So a cubic zirconia, we'll do diamond first, all right? So 2 carat diamond is about $10,000, all right? Moissanite, a 2 carat, so 8 millimeter, that's fairly big, substantial, is about $1,000. Yes, about $1,000. Can you tell the difference between those two? No. But then cubic zirconia, I looked on Amazon, is $11, okay? All right, for a 2 carat cubic zirconia. But, so the reason, they're like, Dr. Ann, I thought you were so cheap, just go with cubic zirconia. But here's the thing, I'm a chemist too. So diamond and moissanite, they're both covalent network solids. They both have very, very high melting points. They both have very, very high hardnesses. The only thing that could scratch a moissanite is a diamond. And I don't interact with those on an everyday basis. All right, versus cubic zirconia, yes, it looks very similar, but it's ionic. All right, so yeah, it's a little bit different. Yeah, it's a lot softer, so it can get scratched easier, but it has similar melting points there. All right, so me personally, I like moissanite. My eyes cannot see the difference between here. All my jewelry is moissanite, because then I can afford bigger ones. Right? Yeah. Okay. But let's look at the structure of these as well. So we looked at the similarities in properties, the differences in price, but let's look at the structures. Let's look at the hybridization of a carbon atom in diamond. So how do we do hybridization? We count what? Electron domains. So we want to look at one carbon atom, ask ourselves how many electron domains are around that carbon atom, and what would you say? 4. 1, 2, 3, 4. So what's that hybridization? sp3, great. So here is the unit cell of moissanite, hexagonal. So let's look at this, one of the atoms, the easiest, look at this atom right there, the green one. What's its hybridization? How many things are attached to it? 4. 1, 2, 3, 4. So what's its hybridization? sp3. Okay. What about the oxygen in cubic zirconia? So look at that red atom. How many things are attached to it? 4. So what is its hybridization? sp3. Yeah. So there's a lot of similars and even microscopic structure here of diamond and diamond alternatives. All right. And a difference in prices. So hopefully the De Beers company doesn't come cancel me. But that's why I buy moissanite. Okay. One last thing. So actually, I chose my own engagement ring. Yeah. And so my engagement ring actually isn't, it is moissanite, but the main stone is actually alexandrite. All right, so alexandrite, it goes by this thing, they call it emerald by day, ruby by night. Right? And so this too is an ionic solid. It's aluminum with beryllium with some chromium impurities to make it this color. And so what makes this gemstone really interesting is depending on the kind of lighting that you're in, it changes color. Right? So that's why they call it emerald by day, ruby by night, because it changes color depending on the light that is available for it to reflect. Right? So if you're asking, like, was I a mood ring girl in high school, you would be right, I was. All right? But I wanted to bring this up because there's actually some review that we can do. The reason alexandrite changes color in lighting is because it has 2 absorption bands. Right, in the visible spectrum. It has 2 absorption bands, meaning it absorbs these energies of light. And so depending on the composition of the white light around it, so here this is daylight where there's a lot of blue light present, and it will look more blue or green. Versus incandescent light has a lot of red in it, and so the light that's mainly reflected makes it look like a ruby. Really, it looks like purple. Mine does. Right? So that's why it's different colors. But let's review a little bit. So if these peaks are absorptions, this is the light that alexandrite absorbs. Tell me, which peaks, A and B, correspond to which of these transitions on the electronic spectra of this atom? This is review. This is chapter 6 review. All right? So we have band A and band B. Note where those energies are. So remember, energy of a photon, as it increases, typically we see wavelength, how does it change? Wavelength, as energy of our light increases, wavelength gets shorter, yes, but frequency goes up. Okay, great. If these are absorption bands, that means light is absorbed and the electron goes where? Up. So which one of these can we eliminate off the bat? 2 and 4. Those ones emit light. So now we're looking at transitions 1 and 3. So which one is A and which one is B? Transition 1 is high energy, so that would relate to what kind of wavelength? Short. So which one's that, A or B? A, yep. And then 3 would be B, because it's smaller energy, longer wavelength, so this band, the absorption band, is at lower energy. Yep. And so those are the 2 transitions that are in my engagement ring, or whatever. Okay, so that is alexandrite. Gemstones. Typically we see are ionic solids or covalent network solids, because those have the properties we want in gemstones. We're never going to see molecular solids as a gemstone. Why? Molecular solids have what property? They're soft. They dissolve in water. Do we want that as a gemstone? No, we don't, okay? So here's some examples of some of the gemstones. A lot of the colors we see are because of impurities. We take an ionic solid or something and we just add some metals and it makes it these beautiful colors. All right, so those are gemstones. All right, so what else can we talk about ionic solids? Melting points. We didn't talk about melting points of ionic solids. But thankfully, it relates to something you already know. Melting points of ionic solids trends with lattice energy. The stronger the lattice energy, isn't it the harder it is to rip the ions apart? So shouldn't it be harder to melt it? So as long as you know the trends with lattice energy, then you can predict melting point temperatures as well. As the magnitude of lattice energy increases, melting point increases. So it's the same exact strategy. We want to review ion charges and ion size if the charges are the same. So if we look at these 4 compounds, let's order them in increasing melting point. What we're looking as increasing lattice energy as well. That's it. So we already know how to do this. So lattice energy, we look at charges first. So magnitude of charges. So we have +2, -2 for magnesium sulfide, +2, -2 for magnesium oxide, +2, -1, +1, -1. So which one has the lowest melting point? NaCl. NaCl is the lowest because it has the lowest lattice energy. Next. MgCl, 2. Yep, because it's +2, -1. And so then these two, magnesium sulfide, magnesium oxide, are going to be the highest. But how can we distinguish between those? Size. But how does it trend with size? Which one has the higher lattice energy? The ions that are bigger or smaller? Smaller. Smaller ions, more attraction, higher lattice energy, higher melting point. So of these, the two differences here are the sulfur and oxygen. So those are the ions you want to compare. So which one of those has the highest melting point? Magnesium oxide, yes, because it's smaller. So it's MgS and then MgO. All right, so that's just review. That's just review. Right, melting points of ionic solids trends exactly with lattice energy. Okay. Okay. So let's talk about how we can structure ionic solids. So ionic solids differ from covalent network, metallic things, because we're working with ions and packing them in a closed space. So ionic solids, when we form them, we need to make sure we maximize attractions between cations and anions, but minimize any repulsions between two cations or two anions. So there's this additional factor when forming ionic solids that we didn't have to think about for like covalent network or metallic solids. This is additional idea, and that's why we get a lot of shapes that we do, right? So let's look at this picture, all right? This is, again, a lot of review. A lot of chapter 12 has review in it. Based upon these pictures, I have a picture of like a purple particle and a yellow particle. So if we remember, an ionic compound is always a cation and an anion. Which one of these is the cation and which one is the anion? The purple particle is most likely to be what? The cation or the anion, you think? The which one? Anion. Why? Did you guess? 50-50. Well, then how did you know that this one's positive? Okay, so you're right that the purple one is the anion. But anions, when you make an anion, if I have fluorine and I make it an anion, it becomes bigger, yes. Versus cations, when you remove electrons, they become smaller. So the purple is most likely the anion, the yellow is most likely the cation. All right? Okay, there we go. All right, so with that in mind, if these purples are the anions and the yellow is the anion, which of those pictures, A or B, is more stable? A or B? It is not A. I know, A looks nicer, doesn't it? It looks nice, but think about it. A has two anions bumping uglies. Oh, yeah, even though it looks nice on our eyes. Versus B, aren't all of the anions touching the cation, but the anions aren't touching one another. Right? So actually, the more stable particle is B. This is a homework question that does very poorly. Right? So A is not stable because you got these anions bumping uglies with one another. Okay, all right. So how we can predict how ionic packing occurs depends on the size of the cation and anion. That's what we're going to learn here. And so how we can determine and like predict what kind of packing occurs, we want to look at the relative difference in size between the cation and anion. So this is where we look at what's called the radius ratio of the ions, where we take the radius or the diameter of the cation and divide it by the anion. So since cations are usually smaller than anions, usually rho is a number that's less than 1. And so depending on what rho is, what number it is, we can predict what kind of packing we get in our ionic solid. And that's this next slide. All right. So here in this picture, we have 3 different salts. All these salts, like cesium chloride, sodium chloride, or zinc sulfide, they have different rho values. The cation-anion ratio we see goes from 1 and decreases all the way to 0.5, all right, where 0.5 the cation is a lot smaller than our anion. And so what we see is based upon that rho value, we get different ionic packing within here, all right? There we go. So how else we can look at this packing that's useful for us is looking at the coordination number. How many cations can you fit around an anion? And the other way around too. How many anions can you pack around a cation? And it depends on the relative size difference of the two. So what we see is when the cation-anion ratio are similar numbers, like they're similar sizes, the cation and the anion, when rho is close to 1, we see really, really high coordination numbers. We can pack 8 other anions around that cesium cation. And the same thing with the anion. That anion, I can pack a bunch of cations around it. Versus once we start getting a really big difference in the size of the cation and anion, we see the coordination number go down for these different unit cells. So what is coordination number? It's kind of like when we calculated hybridization and we counted how many electron domains are around an atom. It's the same idea. If you look at this cesium atom, ask yourself how many other atoms, how many anions are around it. There's 1, 2, 3, 4, 5, 6, 7, 8. So cesium has a coordination number of 8. So it's very similar to how we did hybridization. You could look closely at like one of the sodium or chlorine atoms here. If you count the other ion, there's 6 of them around it, all right? And so yeah, very similar to how we did hybridization. That is how you calculate coordination number. So the trend is usually as rho approaches 1, that's where you get the best, highest coordination numbers when the ions are similar in sizes. All right, there's a homework question that's kind of tricky here that I want to help you with, where the question gives you coordination numbers and wants you to predict what the formula is. Right, so remember, coordination numbers means how many of the other ion is around that atom. So let's look at this. If our cation has a coordination number of 4, that means there's 4 other anions that are adjacent to it in the unit cell. If another anion has a coordination number of 8 in the same unit cell, that means that there are 8 cations adjacent to it in the unit cell. So based upon this information, what is the chemical formula or empirical formula of this salt, if given the coordination numbers? Cation with a coordination number of 4 has 4 anions. An anion's coordination number of 8 has 8 cations. So what we want to do is take what atoms are present in the unit cell. So it looks like there are 8 cations and there are 4 anions inside this unit cell. But is that a ionic formula that we typically give? No, we can simplify this, right? This would simplify into, 2 cations for every 1 anion. So the correct formula would be this one, M2X, where there are 2 cations for every 1 anion. And that's kind of weird because if you look at this, it says, cation coordination number is 4, but that means there's 4 anions around it. An anion's coordination number of 8, that means that there are 8 cations around that anion. So we kind of have to think about it oppositely, but that's the strategy there, all right? Okay, so we'll stop there because the last learning objective that is on the final exam is this last slide, and we'll finish it on Tuesday, is how to look at a unit cell and predict empirical formulas, right? Okay, so chapter 11 homework is due on Monday. We'll finish these last slides on Tuesday.